Okay, so all right, example 4 is kind of bringing this all together, finding the slope of the curve at 3, 9 if the equation is f of x equals x squared, which of course 3, 9's on there. All right, turns out we're not really going to use the 9 all that much. It's really all about x, but you'll see that. I mean, because everything that we deal with typically is. So what we're looking for then is f prime of a. All right, and f prime of a, with a being a particular value, 3, and we'll deal with the 3 at the very end. All right, so just for right now, I'm going to say that we are trying to find f prime of a, the slope of the tangent line to the curve of x squared when x is equal to 3. All right, so let me just let's go over to Desmos just real quick and take a look at that. All right, so when x is 3, we're right here. So we're trying to find the slope of this line right here that is tangent. So it's going to go something like that. All right, that I missed, but you get the idea. All right, so that's what we're looking for. All right, well, as we just saw, f prime of a, the slope of the tangent line at a particular point, is equal to the limit. We haven't done that yet. As h approaches 0 of f of a plus h, which we just did four of those f of a plus h's, minus f of a. This is y2 minus 1, y1. And then, of course, x2 minus x1 is just h, because that's how far down the line we went to draw our secant line. All right. And so we would like that h to go to 0 so that we can know exactly what's happening at a f of a, which in this case is 3, 9. All right. So on this particular function, that's going to be the limit as h approaches 0 of, now, so I'm taking, this is y2. I'm substituting that right there into x squared. And so I'm going to have a plus h squared minus y1, which will be, I'm about to write the same thing again. Sorry. F of a, which is a squared. Okay. And then you're like, how is this even going to help us out? Well, just watch the magic that happens. It's the same magic that you've been dealing with before. Like things are going to work out. Like right now, I still can't evaluate this limit, because if I substitute in the 0, a 0 there gives me a squared minus a squared 0. It's 0 over 0. But 0 over 0 is oftentimes good news. Okay, because then there's some kind of magic that's going to happen. All right, so let's check out that magic. So we've got limit as h approaches 0. All right, my numerator, here we go, is a squared plus 2ah plus h squared minus a squared. Now, here's what I typically like to say. Anything without an h should cancel, should go away at some point. And the reason that needs to happen is so that then, if we're truly able to do this, and we've seen every single time that you can, if we're truly able to do this, then I should be able to cancel this h with remaining h's in the numerator. That's exactly what's about to happen. Because check this out. A squared minus a squared. All right, so I can continue with this. And there's some steps you can skip along the way, but you do want to show as much as you can to show that you know what's happening. All right, so up top, and here's what I'm saying. Like, you probably could say, all right, that h is going to cancel with that h and one of those, and that's fine. But I'll show it in the factoring way to do it. I mean, it's the same thing, but again, I really do strongly believe that you could skip this one I'm doing right now and go to this one and be totally justified, because you're just saying I divided both of those things by h. So if I divided both of those things by h, then I've got this, the part I had in the parentheses on the last step. And I kind of like this right here. Just, I don't know, maybe not necessary, probably, but okay. All right, so there we go. And now I can evaluate this limit, because all I got to do is send h to 0. Well, if I send h to 0, then that will become 0. Again, unnecessary step. It's 2a. So that's the deal then. So every single time you're looking for an instantaneous rate of change on x squared at a particular a value, it's going to be 2a. I mean, we just proved it. It's 2a every single time. So for this particular one then, so I could say then, therefore, f prime of 3 is going to equal 2 times 3, and it is 6. So we just found an instantaneous rate of change by using what we algebraic technique and knowing what the and using a very specific version of the slope, okay, and then sending the run, it's rise over run, sending the run to 0, okay, and you couldn't do it to begin with, couldn't do it at this point, still couldn't do it until we had this step right here where, and I never did really show it, and I should have, where those two cancel out, right? And once that's happened, and you've seen it numerous times, once that's happened, you then can evaluate the limit and find the instantaneous rate of change. That's pretty awesome, okay? What are the uses of that? Okay, how about every single engineering that exists? Okay, how about all kinds of stuff? All right, you finally reached a point where I can like in Algebra 1, they're like, when are we ever going to use this? And I'm like, But now, oh my gosh, the uses are boundless.